Okay, hello everyone. This is our second meeting in this course on diffusion. What I'm going to do now is to go back to the very same chapter we left last time, the background chapter. Let me remind you, this chapter contains three pieces. The first part where we discuss the importance of P of X, the probability density function of images, and how great it would have been if we could have held this function in our hands. The second part talks about the evolution of P of X, how actually people came up with guesses for P of X over the years in the classical era, and that applies to 10 years ago and before. And the third part is about the deep learning revolution and what happens then in this quest. So we covered the first third. We started the second. I'll come back to it and we'll take it from there and proceed. So let's go on. Okay, so the end of the first third was the fact that we asked what P of X is good for, this PDF of images, and we answered that it is actually great for many things. It can serve many tasks in image processing. And hey, by the way, everything I'm saying here applies to other signals, other data sources as well, of course, with the proper adjustments. And the immediate follow-up question was, okay, so who is P of X? What do you do about it? And that brought us to the second part of the background chapter, all those guesses about the choice of P of X. And we did a bunch of such guesses, and let me just recap for you. One of the early ideas that came up was that let's believe that images tend to be smooth. And so smooth images are likely to be non-smooth images should be assigned with low probability. And this is exactly the expression here. An exponent of minus c times the norm of the Laplacian over the image squared. Basically, if the image is smooth, the Laplacian of the image is a vector with many zeros or near zero values. You square them up and you get a high probability. If the Laplacian creates high values, then the image is probably not smooth and therefore not likely to happen. This was one such guess that took place in the early 70s and all the way to the 80s. A parallel guess of a similar flavor was using transforms. Fourier at the beginning, later on it was 2D DCT. The idea was when I'm doing a transform on images, I'm expecting the coefficients to be dominant in the low frequencies and nearly zeros elsewhere. So let's actually force it as a way of quantifying the probability. And this brought this guess. So two guesses, and then came the third, which is so natural. People said, hey, this is Gaussian, and this is Gaussian as well. So if you believe that images are Gaussian, why not just fit a Gaussian to your data? And so this brings us to the PCA or the KLT. It's not much smarter than the previous two. It is replacing the guessing of L here or T here or lambda with a numerical matrix R that draws its content from actual images, which is better, of course. But since images are not necessarily Gaussian, then all those guesses are actually quite poor. And I commented about the fact that the PCA or KLT is actually almost aligned with the transform option when you work on 2D patches of size 20 by 20 or 10 by 10, which explains why JPEG is so good in working with these patches and with this specific transform. Lovely. Realizing that images are not Gaussian, and how do we realize that images are not Gaussian? Simply because we deploy those priors, and the results we get in all sorts of algorithms are very poor, which means that our assumptions are actually wrong. So people started deviating from the Gaussianity and searching something else. And one of the first thing that people did was to move to the weighted least squares, the weighted L2. The idea is the following. This is, by the way, still Gaussian. This expression says the following. Yes, I'm going to assess the image by its smoothness, but if I have some clue where the edges are, let's give them a discount. Let's not force them to be smooth. And so pixels that have a possibility of belonging to edges, let's give them a low value in the diagonal of W. Okay, so W is a diagonal matrix. So this is weighting. And if you do that, you get the weighted least squares or weighted L2. And people worked with it, which was definitely better. But hey, this is still Gaussian and it's still poorly performing. And then we are getting into the the 80s and the early 90s, and people starting to realize that we have to move away from Gaussianity. And the way to do so came in several directions. And there is a common theme to all of them like this. So a family of algorithms came from partial differential equations. And what they did is to bring all sorts of alternative measures of smoothness. For example, total variation. Total variation is basically the sum of all the gradients, the length of the gradients in the image. It's an L1 measure. And it is already working way better than the previous approaches. It is no longer Gaussian. A parallel approach, which is very similar to what we did before, is to replace the L2 with L1. Such a delicate change and such a dramatic difference in terms of the performance. Here, you are not squaring the Laplacian values. You are basically taking them in absolute value and summing them. And if you do that, you end up with better performance. So, robust statistics. Another breed of methods stated that if you do apply a wavelet transform, no longer a regular transform like the DCT or the Fourier, you do expect some specific behavior, but no longer concentrated in low frequencies, but rather separated between dominant elements and non-dominant elements, wherever they are. And this is the L1 option, the sparsity over the wavelet coefficient. Now, what do we see here? We see here that all those distributions are no longer Gaussian. In fact, they are heavy-tailed in the sense that they are wider in their distribution. And we are migrating from L2 to L1, L1 here, L1 here, L1 here. And all these options, if you plug them into restoration algorithms, you no longer have a closed form solution. You do have to iterate in order to get a solution, which means that you come up with all sorts of nonlinear filtering algorithms. And it created a terrific field for a decade of lovely algorithms and optimization methods and highly successful algorithms. The evolution proceeded with better and better methods. The more recent techniques is the field of experts that is very similar to the Laplacian approach, but simply saying, hey, why apply a specific Laplacian? Why not learn it? And why apply L1? Why not learn this as well? And why apply just one? Maybe apply a group of them, and this will be the prior. So this is yet another option. Another option, which I will not discuss here, I spent something like 15 years on this option, is the sparse representation approach, where you work with L0, not even L1, and a learned dictionary. A lot can be said about this, but it doesn't have any connection to our course here, and this is why I will give it at that and move on. So a lot of options. The recent ones are more learning-based, and sparsity becomes a key in whatever we do. And here is the overall evolution. And what you see here is a general trend from L2 to L1 or even L0, and from choosing or guessing to learning and adapting to data. This is the trend that took us from the 50s or 60s all the way until 10 years ago. And then we got stuck. Okay, so this evolution of priors, I want to say something about it. I don't know if you noticed. Look at this again. All my choices here are exponent to the power of something, okay? Exponent to the power of something. This is known as the Gibbs form of the distribution. You have to understand that there is no loss of generality in assuming this structure. Any probabilistic function can be described as a normalizing constant time exponent of some minus energy function. And so we are focusing on rho of x instead of p of x. And so the evolution that takes us all the way from this dumb idea of norm, which is leading to the pseudo inverse of the degradation matrix, to smoothness, to weighted smoothness, to robust statistics, to total variation, to wavelets, to sparsity, and so on and so forth. All these are simple cases of choices of this rho function. Okay, so just to summarize, and with this I finish this part. 5 decades of massive work in choosing or learning P of X for images, and many algorithms that evolved from it. All of them looking at this Gibbs form, searching for the function rho of X with some parameters theta. Very much missing in those many years of activity several critical things. First of all, almost no work dared to look at this coefficient here and ask, what is it? In fact, even a more fundamental question was not asked. If you choose a specific energy function here, are you sure that your expression will be integrated into a finite number so that it is a valid probability density function? You don't know. And one last thing on the practical side, if you are guessing some sort of P of X, can you synthesize images from it? Can you actually create images that follow this distribution and convince me that those are good looking images? Nobody did that. And yet, a lot of work, many algorithms, quite successful ones. In fact, many of the algorithms that work today in products on image processing are relying on exactly that, on those choices of raw and whatever emerged from them. So there are good things to be said about this past work. 10 years ago, as I said, all these got stuck. And so let's see where it takes us. Let's move now to the deep learning era. I think that this part of the presentation will be more appealing to you. Okay, what is the claim of fame of deep learning? At least in the beginning, in the paper by Krzyzewski, Sotskover, and Hinton, it was classification of images in a supervised approach. Here is the idea. You are designing a neural network. It has to be deep, such that it will get an image in the input and it will produce a classification in the output. You typically rely on a data set of images and their labels. Let's make it concrete. If it is ImageNet, then we will have capital N being 1 million images. Classes could be 1 of 1,000. So capital C here is 1,000 possibilities. And every image is assigned with a class. It could be a dog, it could be a plane, it could be a car, etc. How do you train such a machine? You train it by minimizing this loss. Basically, you convert every one of those labels into one hot vector of length capital C. So it will be of length 1,000, where only one element is 1 and all the rest are zeros. You look at the output of this network, which is an output of 1,000 probabilities. This is the softmax values. And you basically say that those softmax values should be close to the one hot vector they correspond to. And you measure the distance using Kullback-Leibler and cross entropy. And again, the claim to fame in 2012 and beyond was that these machines are already working amazingly well, bringing accuracies that we have never dared before, okay? By the way, in the original paper, the accuracy was 17% success, or 30 if you look at the top 5. Today, we talk about 90 and beyond percent success. Yes, it is working. This is the original claim to fame. This is happening in 2012. In 2012 or 13, people are starting to do something else, which is also daring. Supervised learning still, it is a regression kind of work. Machines that convert one image into another. For example, imagine that I have a low resolution image here and I want to convert it into a high resolution image here. So we have a network that does the super resolution task. How do you do that? Again, a training set of many, many pairs of low res and high res pairs of images. And again, it could be for deblurring, denoising, super resolution, whatever you want, all those problems and many others. And again, you train with using a loss that says, hey, the output of the machine, if you feed it with YK, it should get as close as possible to XK, and the loss is typically L1, L2, something of this sort. Okay, so these are the two commonly played with neural networks that we are familiar with. And then in 2014, something else came up, something else and quite fascinating. Sampling from the probability density function of images using examples. The idea is to train a machine like this, that will get a random seed in the input. It could be a plain Gaussian vector, IID, normalized Gaussian. And this vector is converted by this learned machine, which is a neural network, into a good-looking image. And the idea is you bring me many, many images, good-looking images that are basically many, many samples of P of X. And this machine is supposed to understand what P of X is and provide new samples of it. Okay, this is the idea. And again, Z itself could be a very simple Gaussian vector. It's typically the assumption made, and the output here should be a fair sample from P of X. Now, many questions arise when you look at such machines. How do you train them? What is the loss in order to make this work for us? Can it do more than just generating images? Can it, for example, can it give the value of P of X? This will be amazing. Can it be service to other tasks like inverse problems? I mean, can I use it once it is trained to solve other image processing problems? And beyond all this, suppose I give you such a machine. How do you assess whether it is good or not? How do you know whether it is delivering? What is the quality of the output? Let's answer all these questions in the following slides. Okay. And by the way, this line of work started in 2014. It's amazing. Many papers in different directions, all of them coming in 2014 and addressing the same question of designing this G theta. So let's talk about this G theta. Just before that, let's talk about the core idea of synthesizing images. Again, from 2014, we are obsessed with hallucinating images, creating images out of thin air. It's typically going hand in hand with GANs, but it's not the only approach. In fact, diffusion approaches are far better. These are images created by a specific GAN. Look at the images, hallucinated, and yet they look perfect. Look at these people. They do not exist. They are taken from a webpage called thispersondoesnotexist.com. And the question is, why are you bothering synthesizing images? Well, in the spirit of what I've explained so far, if you have a machine, of course, it's fun. Obviously, it's fun to create a machine that generates images. But beyond that, if you have a machine that can generate amazing looking images like this, it really means that it captured P of X in some way. And that means that you can leverage it to do image processing, which is exactly what we are after. Okay. So who are those algorithms that can provide samplers from P of X? There are many such variations: variational autoencoders, GANs, generative adversarial networks, normalizing flow methods, recursive methods, energy-based methods, and the most recent comer to this game are the diffusion models, which will be the center of this course. So what I'm going to do now is to dedicate a few slides per each of these, and of course the rest of the course for the diffusion models, okay? And let me just make clear that once you have any of those working for you and it delivers good quality images, you can now start playing with it and use it in order to apply it to all sorts of applications. And this is exactly what people have been doing: better compression, better conditional synthesis, better solving of inverse problems, etc. Okay. And just before I'm diving in to these methods, let's say one thing that should be said. You know, I'm cheating here because I kept telling you how important it is to put our hands on P of X. And suddenly I'm changing the question and I'm asking whether I can sample from P of X using a learned machine. I mean, here is one problem: generating a machine that samples from P of X. And this is another goal of putting our hands on P of X. Does one infer the other? I mean, if you have a generator, do you know how to compute P of X? And if you have P of X, can you generate images? The answer in general is no. The two are two different, related problems, but different. And yet, yes, we will go to samplers now because it does have a service, and eventually we will connect the two. But at the moment, please note that we are changing the focus from knowing P of X to sampling from it. Okay, so let's proceed. Let's start by discussing the variational autoencoders. Variational autoencoders rely on autoencoders. The paper that turned autoencoders into variational ones was published in 2014. So let's start with autoencoder. This is an autoencoder. There is an encoder that gets the image in the input and creates a latent vector Z in its output. And there is a decoder that takes the latent vector and converts it back into the image. And a good performing autoencoder will be such that X hat is very close, hopefully equal to X. So whatever comes in here should come out here. We would like all this machine to be a unit machine that basically do nothing. But however, it cannot just do it trivially because Z here is a bottleneck. The dimension of Z is much smaller, typically, than the dimension of X, which means that the encoder is basically doing some sort of dimensionality reduction, and yet you still expect the whole machine to be a unit system, which means that the encoder needs to throw away only redundant content, and the decoder should revive from whatever Z contains the image up to the few missing details, okay? This is the autoencoder in its classical form. How do you train it? you train it using this trivial loss that says output, hey, be equal to the input. So if you feed xk to the input, you have capital N examples. If you feed the image xk to the input, you apply the encoder, you apply the decoder, each with its own parameters, phi and theta, and you ask the distance between the output of the machine and the input to be the smallest. It could be L2, it could be L1, whatever you want, and you minimize this. And then people looked at this and said, you know what? Once this is working for us, why not just throw away the encoder? Think about the decoder as our generator. Here we have a latent vector. Let's just refer to it as a Gaussian vector. And create a Gaussian vector, feed it to the decoder, and get a good-looking image. What do you think? Could it work? Does it work?
No.
Why not?
Because you have holes in the latent space.
Wonderful. You see, when you train a neural network, and this is a general rule to take with you forever, it will do exactly what you want. And whatever you did not specify, it will not deliver. It will do whatever serves its needs in order to make you happy on your objective. I said nothing here about the organization of the vector Z here. I said nothing about them looking like Gaussian vectors. And they will not be like Gaussian vectors. Okay, so let's be more concrete. We are getting cloud of Z's that corresponds to the cloud of images that we fed. These Z's will be spread all over. They will have holes in the space that you would never visit. Distances will be warped. That means close by images will get very far away Z's and vice versa. All sorts of crazy things will happen. And besides, where is the probabilistic interpretation of Z as a Gaussian? You said nothing about it. So we need to fix it. So people started fixing it, and this brought people to invent the variational autoencoder. And here is what they did. Intuitively speaking, they said, okay, if you want the Z's to organize lovely, nice, make sure that they are all pushed towards the origin. And so here is the intuition that stands behind this sentence. You do the first loss and you add the second loss, and the second loss says something very simple. And dear encoder, once you finish working on the image xk, make sure that the norm of the vector is small. Push it towards the origin. And so when packing everything together, hopefully we will avoid those holes that we mentioned. So this is just intuition. I'll come back to this intuition in a few minutes, and you'll see that this intuition is actually spot on, but let's just forget it for now. The people who came up with the notion of variational autoencoder wanted also to talk about the probabilistic interpretation. And so they said, you cannot go back to an autoencoder like this and claim that this is Gaussian. In order to make it Gaussian, let's change the language. And so here's the new language that they suggested. The encoder will work on the incoming image, produce some sort of parameters. Those are deterministic parameters. These parameters will serve in order to compute a sampling of Z. You'll see in a minute how, very simple. And once you have Z is a random vector. This is the one that is fed to the decoder and you proceed. So now Z is actually a random entity, okay? Let's be more concrete here. No, actually, let's wait for the next slide to do so. Okay. Now let's make things more formal. I want my Z's to look like a Gaussian distribution, canonical Gaussian distribution. I could have assumed a different distribution, but this is one that is very pleasant to work with. So without loss of generality, I'm sticking to this choice. So P of Z would like to be a Gaussian. Okay, now the encoder gets a specific image and it applies whatever it applies to it, and it creates an output. The output is attributed not to a single vector Z, but to a cloud of possible Z's, a small cloud, very small cloud. This image is misleading. It should be a very small spot here. So many Z's in a sphere or in an ellipsoid like this correspond to this image. How? Here is the idea. The conditional probability, don't be alarmed, the conditional probability that the encoder creates for the Z's given the image that it was fed with is a Gaussian. I will assume that every image that is injected into the encoder creates a Gaussian with a specific mean and a specific covariance. The mean itself will be the output of the encoder. The variance itself will be the output of the encoder as well. Notice that I'm insisting on a simple variance as a diagonal matrix. Why? Because otherwise it will be a huge matrix and too many parameters. So basically, I'm assuming that this Gaussian is parallel to the axis. It's not rotated. Okay? So the main diagonal of this covariance matrix and the mean are the two vectors that the encoder produces, and these together induces some sort of a Gaussian that corresponds to the image X. Okay? Every image X will create a different blob like this. And we'll have many, many blobs, each one corresponding to each possible image. And I think you know where I'm going with this. What I would like to get is that the mixture of all the red blobs together will align with the bluish Gaussian underneath. This is what we will try to do. And I'll make it more concrete in a second, okay? So here it is. All we are aiming to do is to make sure that all those red blobs together are creating something that looks like a Gaussian, a one single PZ Gaussian. Okay, let's make it even more concrete. Let's talk about the sampler that I mentioned, this sampler here. Here is how it will work. We have just defined PZ as a plain Gaussian. We have just defined the P phi of the conditional Z given X as a simple Gaussian that each image is converted to using the encoder. And now, here is the idea. Z itself will be created by, you take the output of the encoder, the mean and the variance. You take any random IID vector from the Gaussian distribution, multiply it by the variances, add the mean, and you get a Z with which you proceed to the decoder. This is how you actually guess a point within this small cloud. Okay, lovely. Now, what is it that we are after? Just like before, X hat should be very close to X. So we'll write a penalty very much the same as the one we have written before for the regular autoencoder. The second part will say, PZ, you should be somewhat related to those conditionals. How? Like this. Look at this equation. It's very simple. It says the following. Every one of the images that the encoder works on has a conditional P of Z given X. If I integrate over all the images, I'm getting the marginal P phi of Z. P phi of Z is the probability of Z's as the encoder sees them. All I'll try to do now is to make sure that P phi of Z and PZ are the same or close by. That's all. So how do I force two probability density functions to be close by? I use Kullback-Leibler or Wasserstein and basically squeeze the two to each other by training the parameters phi, which is exactly what I'm going to do now. So I'll use the Kullback-Leibler. Just a second. So this is the Kullback-Leibler between two distributions. Okay. P of Z will play the P, and P phi of Z will play the Q. So here it is. Very simple. Look at it. Integral over all the Z's, P of Z in the denominator, P of X in the denominator, log, and in the denominator, I'm putting the P phi of Z. Now, instead of integral, I'm doing a summation over the examples I have because it's not an integral. It just, I have a training set of 1 million images. This is what I'll use. And I'm dividing this by 1 over n, which explains why we have n here. So if we could have minimized this expression, we could have found the ideal encoder. But people looking at it says, oh, this is too complicated. Let's do something simpler. Let's replace the order between the log and the sigma. There is something known as the Jensen inequality. Or in fact, it's a very simple arithmetic geometric mean relationship that says that arithmetic mean is always bigger than geometric one. So you replace the order between the log and the sigma. The log basically steps in. Look, the log steps in and the sigma steps out. In fact, all the way out of the integral. And then people are very happy. Why are they happy? Because the inner part here is a plain KL divergence between what? Between a Gaussian and a Gaussian. Remember, this is the blue Gaussian and this is one of the red Gaussians. And what's so nice about a distance between two Gaussians? We have a formula for it. So people applied this formula. Here it is. Looks horrible. Don't even bother reading it. All it says is this Gaussian has zero mean. This Gaussian has some sort of mean m phi. It has a variance. This variance is 1. So just use it, and this is what you get. So this is the second term in the loss function. You have one loss that says x hat should be close to x, and the second loss that says let's have this penalty minimized, so that I'm pushing this down. Now observe the following. This is a Kullback liable distance, and as such, it is always non-negative. So it is bounded from below by 0. If you push this down, you are minimizing it. You are also pushing down this. And this is the idea, the elbow idea, the well-known elbow idea in variational autoencoders. Okay? So you minimize a proxy instead of the original expression. And secondly, notice that what we did here is to force the encoder to produce Gaussian vectors, but we said nothing about P of X. We don't know what comes out of the decoder. Something here is very much missing in the analysis, and people try to address it in the literature, but I don't buy their treatment. In order to come up with an explanation for what is the distribution in the output, they had to add yet another noise in the output, which is counterintuitive. Anyway, one more thing I want to say about this slide. Remember that we assumed for those red clouds that they have a diagonal covariance? You know, it's just an assumption. I could have made a different assumption. I could have made the assumption that all of them share the same sphere radius. So basically, all of them will have a diagonal matrix with the same value along the diagonal and the same value for all of them. If this would have been my assumption, then this will be a constant times identity, constant time identity, constant time identity. In this case, this and this fall down, and I'm remaining with norm squared of the means of the encoder output. What is it? This is exactly the intuitive approach I suggested in the very beginning. Just push all the outputs of the encoder towards the origin. Okay? So the intuition that we had there is actually making a lot of sense with a specific assumption here. Okay, let's summarize. Variational autoencoders are working, but they are not truly competitive when it comes to synthesis of images. And there are a variety of reasons for this. First of all, the idea that we force x hat and x to be close by is counterintuitive. And I'll tell you why. We have x at the input. It goes through the encoder. It creates a cloud of z's. And all those z's should get me to the same x. It really means that x must be blurred. And so I'm blurring the output. And by the way, images coming from autoencoders, variational autoencoders, are typically blurred. And this might be one reason for this. So this is counterintuitive. In fact, something even deeper that takes place here, which I will not dive into here, but we will talk about it later on in the course, has to do with something called the perception distortion trade-off. This is lovely work by Tomer Michaeli and Yochai Blau that was published in 2017. What they said is that if you have a machine that you try to train and you force the distance between images to be minimum, this is the distortion. If you force the distortion to be small, you are necessarily paying in perceptual quality. That means the images are necessarily poor looking. This is exactly what's happening here. So here is another reason why VAEs are not necessarily working well. Another reason to suspect our approach is the fact that we assumed very specific structure for these conditionals being with a diagonal covariance, which is not justified, just justified numerically, but not practically. Again, this Jensen inequality that we used for the approximation of the KL has a cost by itself. So for all those reasons and many, VAEs are not working great. But over the years, people come up with all sorts of variations. For example, there is something called GAN VAE or VQ VAE that are already working somewhat better. And in fact, we will see VAEs coming back again and servicing diffusion models. In fact, one of the best algorithms for diffusion is the stable diffusion algorithm, and it is involving VAE. So they can be used in the proper context. Okay, so these were VAEs. Let's move to GANs, generative adversarial networks. There is a question here in the chat. Does comparing PZ to P phi of Z means that for each possible latent vector exists an X that encodes it? Not necessarily, no. But it's not intuitive. Let's move on. GANs, also conceived in 2014, are yet another way of designing, training G theta. The idea is the following. You have actually two networks. The generator that aims to convert the seed vector Z into an image, a good-looking image, and a critic or discriminator, basically a classifier. A classifier that gets an input image and needs to tell us whether this is a real or fake image. And if it is fake image, if it believes it is a fake image, the value will be 0 or close to 0. If it is real image, the value will be 1 or near 1. Values in the output will be always in the interval 0 to 1, pushing to 1 for the good-looking images and for 0, the fake ones. Now, if the critic is able to tell apart true from fake images, it really means that the generator is not doing good work. And so with a proper loss that we will see in a second, you can actually push the generator to lift itself so as to confuse the critic and so on and so forth. So there is a struggle between two machines here. One improves the other, and so they are standing on the shoulder of each other up to the point where hopefully this will produce good-looking images, and this will basically make decisions that are nearly like throwing a coin because it doesn't know. Let's see how it works. Here is a typical loss that people can use, and this is just an illustration of what GANs could look like. This is a very basic approach. I'm taking this concept from Joseph Roca's blog in order to explain the motivation behind GANs. So look at the loss over the two parameters, phi for the critic and theta for the generator. It's a max-min problem. And here is the loss. Very simple loss. Don't be alarmed. The loss says the following. Take many, let's say 50,000 good-looking images, the training images, and this will be this expression. Apply the critic on those images and compute this value, and take, I don't know, 50,000 fake images, basically draw at random 50,000 ZKs, generate images, and compute the critic on those images. Now, here is the idea. Here is another way of writing it down in a more elegant way. I will be using this later on, so it's worth me explaining it. This summation is an empirical approximation of expectation. It's an expectation over the true distribution of images of 1 minus C over those images. And this is yet another summation over fake images. So it's an expectation over the fake distribution of the value of C over those images. Okay, so here is the intuition. Let's freeze G for a minute, and let's optimize with respect to phi, with respect to the critic. Okay, I'm freezing the generator, and I'm searching for the parameters phi to minimize the overall expression. So minimizing this, and I remind you, C here gets values between 0 and 1. So what is the minimum that can be gotten here? These will tend to be 1s, and this will tend to be 0s. Which is exactly what we wanted. We wanted true images to get 1 values and fake images to get 0 values. So the critic will be trained properly to separate between true and fake images, as we described. Now freeze the critic and train the generator. What do you do now? Of course, when you train the generator, this term has nothing to say. It is not dependent on theta. And now you are saying to the generator, hey, change yourself so that these values are maximized, going up to 1. Basically mislead the critic, create images that the critic think that they are good looking. And so the generator lifts itself to better and better looking images. And of course, you iterate between the two forces, and this is what you do. Let me illustrate, and again, this is taken from Roca's blog. Let me illustrate how this could work in this specific case in a toy problem. The idea is the following. Remember, this is the expression we wrote. Here it is written explicitly as an integral, 1 minus C times P true plus C times P fake. Now let's play a game. Let's assume that C here is not even a parametric function. It's a function that can assume anything. In fact, forget about the integral. I'm giving you a specific image. Look at the expression inside the integral. I'm giving you a specific image. You don't know if it is true or fake. You compute P true on it, you compute P fake on it, you get two scalar values, the probability of it being true, the probability of it being fake. And now I'm asking you, you have the freedom to choose C, any value between 0 and 1. What should you choose for C in order to minimize this expression? Please help me. What should C be, a value between 0 and 1, to minimize this expression? Forget about the integral. Any idea? Let me give you an example. You know what? Assume that P true is 0.1 and assume that P fake is 0.1 as well. What would you choose for C?
Half.
You could choose half. Anyone for a different value? Does it matter in this case? Does it?
No.
No, it doesn't. If the two values of the probabilities are the same, you don't really care because it's a convex combination of those two numbers. So basically, whatever you choose for C in this case is okay. Okay, now let's move on. What if P true is truly much higher than P fake? That means the image seems very true and seems very not fake. What would you choose for C? Remember, I'm trying to minimize this expression.
Close to 1.
I'll choose it close to 1. I'll choose it 1. Because if choosing 1, I will null all this expression and I will choose the P fake here because it's the smallest one. Here is the rule. For minimizing this expression, if P true is smaller, go for 0. If it is bigger, go for 1. Never go for the middle. Don't even bother. Okay? By the way, if I go for this rule, what kind of expression remains here? What am I actually doing? Any idea? What remains after I'm plugging in this C inside here? What do you think?
Just the minimum probability.
Wonderful. So we'll go there. So here is the rule that we come up with. P true, P fake for an X that would have been a scalar, just to illustrate. So whenever P fake is dominant, go for 0. Wherever P true is dominant, go for 1, which is, if you think about it, exactly what I told you. I want my critic to tell me 1 for true images and 0 for fake ones. And again, if I plug this into the expression, I'm getting exactly the minimum of the two values per each X. So this is the loss once we have trained the critic. Now I'm trying to maximize this expression. Maximize with respect to what? P true is fixed. It's the true distribution of images. P fake is governed by the generator. So I have freedom to design P fake. What is the P fake that will make this expression maximal? What do you think? What is the P fake that will make this expression maximum?
P true.
P true.
Why?
Because then the minimum between P true and P true is
Exactly. Right.
P true.
You see, if P fake will be always larger or equal P true, then we get the maximum, which is integral over P true dx, and that's it. Okay? But P fake cannot be always bigger than P true because it is a distribution. It must sum to 1. And because of that, it must be equal to P true. So what am I telling you here? I'm telling you that with this intuitive loss, we are getting an intuitive classifier that is the optimal classifier, intuitive critic, which makes a lot of sense. And it leads to the proper distribution in the output. Okay? The next slide does the very same thing for yet another loss that involves, let me see if it comes. A second. Wow. Okay. So here is a loss that is more typically used with log functions, log of 1 minus c, log of c. And if you work with this, then the min and max change order. And trust me, it's the same analysis. You take this expression, you minimize it with respect to c by taking derivative, and you get, and here is the derivative. So basically P fake divided by 1 minus c with a minus, P true divided by 1 by c. You compute the c and you get this. Here is the decision rule, somewhat more relaxed. You plug it in and you get this expression. You look at this expression and you discover that what you see here is basically sum of two Kullback-Leibler divergences, a divergence between P true and the average, or P fake and the average. And by minimizing the two, you are essentially forcing P fake to be equal to P true. So the very same analysis. It's not that important. So let's move on. So I'm summarizing for GANs. GANs are considered as good generators of images, working quite nice. But they are coming with a lot of issues. especially when it comes to training. It's quite challenging to train a GAN and know exactly what you are getting. And this is because of this adversarial loss that is complex. The choice of the architectures for the critic and the generator are critical, and they do influence whatever you get. And here is something very interesting that took place in recent years. The better GANs are big GAN and style GAN. And the better the GANs, you will see something very interesting happening here. Look at this architecture and don't bother with the details. Look, here is Z here, squeezed as the input, going through many, many steps. But notice that within these steps, you keep injecting noise, additional noise. So it's not that you just inject noise in the input, you inject noise in the middle of the generator. And why am I mentioning this? Because later on, we will be talking about diffusion algorithms. They will have the same flavor. Noise will be injected all over the place, not just in the beginning. And maybe this explains why diffusion and GANs first have a connection between them, and secondly, why they use this motif in order to get better synthesis. So this was the story about GANs. Let's move on. Let's talk about flow methods. I'll talk about flow methods for a few minutes and then we'll take a break. Okay, so here is a basic formula from probability theory. It goes like this. Imagine that you have two random vectors, x and z, and obviously they are with accompanying PDFs, px and pz. Now imagine that they are actually related to each other in a deterministic way. So there is a function f that takes you from z to x. In fact, this function is invertible, so you can actually reverse it and go from x to z. It's a one-to-one mapping, which means, by the way, that the vectors are of the same length, as otherwise it could not be. And obviously, P of x and P of z must be related to each other, right? And the question is how? And there is a formula for it. People developed a formula. By the way, developing this formula is not that hard. Here it is, looks horrible, looks ugly, but this is the formula. Here is a more civilized version of it. And what does it say? It says the following. You know, you want to know what is the probability of a specific vector x? Take the z that correspond to it, compute the probability of that z, and multiply by a correction factor. It's a scalar. All this animal is a scalar factor. And this scalar factor says, take the function f, take its derivative with respect to z. Now, f is a function that converts a vector to a vector. The derivative of this function is basically a matrix, a square matrix of size n by n, if those two vectors are each of length n. So you compute the matrix, you compute the determinant of this matrix. It's now a scalar, absolute value, invert it and multiply by P of z, and this is the probability of x. Few comments. First, x and z must be of the same length, n. This Jacobian here is a square matrix that needs to be computed, as otherwise you cannot do anything. And if you are so lucky that the determinant is 1, then basically P of x is P of z, and that's it, which is a great situation to be in. Okay, lovely. So this is the formula people started playing with in 2014, and they said, let's make it work for us in synthesizing images. The idea is the following. Let's design g theta of z such that it starts with a Gaussian z, and it converts it into an image that is sampled from P of x. So we are converting one density into another using a deterministic function g theta. This is our f here, okay? And of course, z will be of the same length as the image in order to make things relevant for the discussion that we have here. And let's do so while making sure that the neural network g theta has determinants of Jacobians that we have control over, as otherwise we are dead, okay? And we will see how. So our goal is to start with a Gaussian vector and transform it into the probability density function of images so as to match the distributions exactly as we wanted for the generator. And this leads to a family of papers that are called normalizing flow methods, again, starting in 2014. 2014 was a miracle year for image synthesis. Let's dive a little bit into these methods. So how do we train G? what we do is to use maximum likelihood. The idea is the following. I'll have, let's say, 100,000 training images. Let's train the machine to make the probability of those images maximum. So the probability of all those 100,000 images should be maximal. Now, since these images are drawn IID from the distribution of images, then the joint probability of them is in fact the individual probabilities multiplied, okay? And those probabilities, instead of maximizing their multiplication, I can maximize the sum of their logs, okay? So remember, I'm just searching for the parameter theta that define the probability here. And now I'm plugging this formula. Look, don't be afraid. The expression is ugly, but it is doable. Here is what I'm saying here. We will take every one of those images, feed it to the function f-1. Look, f-1 is the reverse of the generator. I'll feed it to the reverse of the generator, get a vector. I will feed it to the probability density function of Gaussians, canonical Gaussians, multiplied by the correcting factor of the same function f, same generator, and this will be the probability of that image to exist. And by maximizing this with respect to theta, theta is hidden in f here and f here. By doing so, I'm actually squeezing the generator to make my images most likely to exist. Okay, you might wonder, why won't it go to the trivial solution? I mean, it could create a situation where everything is of high probability. It cannot, because this probability has to integrate into one, because there is a one-to-one mapping between the x's and the z's. So if I'm giving high probabilities to these images, then there must be other images that have low probability, okay? But if you are interested in even pushing this force even stronger, you can actually bring noisy images and say to this loss, make them of low probability. So you can regularize whatever you do here. But this is just a side comment. So how do flow methods work? We have to design G theta, and we have to design G theta such that it is invertible and such that it has a controllable Jacobian. How do you do that? First, we do it by breaking G of theta to layers, to chain of operations. And so the Jacobian is actually a multiplication of all the Jacobians. So if I'm controlling every chain at a time, I will have control over the entire machine. Every one of those chunks should be invertible. Every one of those chunks should be with a Jacobian I can easily compute, and I know what I'm doing. So for example, if the layer is linear, then it should rely on a diagonal matrix or triangular matrices or a permutation or orthonormal matrices. All these are matrices that have, excuse me, that have clear inverse and clear Jacobian, and I'm under complete control. And then, of course, I can come up with all sorts of nonlinearities that are also controllable. Let me show you one such nonlinearity that people played with. It's called nice. It looks like this. You take your vector z, and you break it arbitrarily into two pieces, z1, z2. And you apply the following machine in order to convert it to the next layer. Z1 is simply copied to Z2. So to X, Z1 is simply copied to X1. Here it is. X1, you are equal to Z1. And X2 is Z1 going through a neural net that is learned, and Z2 added to it. So Z2 plus neural net over Z1. The beauty about this network is that the Jacobian of it is 1, easily seen because this is a triangular matrix, and it is easily reversible. If you have the x's and you want to go back to the z's, all you have to do is the following. From x1, go back to z1. Here it is. x1, inject your value to z1. And as for z2, you push x1 into the neural net, subtract x2, and get z2. So it's invertible and with a controlled Jacobian. And people came up with all sorts of similar tricks and came up with neural network that are, bottom line, invertible and with clear Jacobian that can be computed. Lovely. Just to summarize, normalizing flow are not competitive when it comes to synthesis of images. They are competitive in other domains of lower dimensions, for example, molecules and other related low dimensional vectors. But they do bring benefits. Before the benefits, the limitation of normalizing flow are coming from the limited architecture that is forced on us, and the fact that the dimensionality of z and x must be the same, which might be a limitation. The benefits of normalizing flow is the fact that they are much easier to train. The fact that they are not just generating g theta, they are also providing the inverse of it, which is amazing. Sometimes it has a great uses. And another thing, most amazing, is the fact that normalizing flow do not just produce synthesis, they can give you the probability of your image. So it's not just synthesizing an image, it gives you the value P of X, which GANs and VAEs cannot give. And here as well, there are all sorts of variation and extensions, but we will not talk about it. Let's take a break of 10 minutes and continue afterwards. Okay, another breed of methods that come to generate, to train such generators are the energy-based methods. And let me tell you, we are not going to discuss them so much. Why? Because they are somewhat related to diffusion models, and as such, I prefer just to defer this and talk about diffusion methods when time comes. But I will say the following. Imagine that we could train a machine that gives us the value log of P of X, okay? So imagine a machine that gets an image and somehow evaluate the probability of this image to exist or something proportional to it, like the log of P of X. This will be a lovely thing to have. Now, I remind you, in the Gibbs form that we so much love, it's 1 over the normalizing factor, the term known as the partition function, times exponent of minus rho theta of x. So basically, by training a machine to compute log of P of X, log of P of X is essentially designing a machine to evaluate rho of theta. Up to a constant, it's rho of theta. So this is what we are after in EBM's method, energy-based methods. And we can pose it as a maximum likelihood as well. Let's do that, just to show you the elements of it. So here it is. Just like before, let's train the machine so that it gives maximal value to the existing images that we have in the training set. So here it is. I'm maximizing the sum of the log of the probabilities of the training set. And since every one of those logs is, here it is, it's, remember, it's log of z with minus and minus rho theta. So instead of maximizing, it's minimizing log of z plus the sum of the energies. Now, if it could have been done that I omit the first term here, it would have been so easy. Just train a machine that maximizes the values at the output for the given images. But this is wrong, because this is critical. Then you get actually trivial solution. Because if you just maximize the output of your neural network for the given images, it will maximize the output for everything. The normalizing factor here is critical in order to make things sensible, in the sense that for other content, it is not giving high values, just like we had in the normalizing flow. So something is very much missing here. The treatment of this expression here, which is a nightmare, this partition function. And so all the EBMs are basically searching for techniques to avoid this or to compute it in some way using importance sampling or score-based learning. Remember the name score-based learning, because it is the central idea of diffusion models, or Markov chain Monte Carlo. All sorts of techniques, all of them come to make sure that this expression is not neglected. Okay, so this is why I'm not speaking about energy-based method, because if you take the score-based approach, you are almost touching diffusion. In fact, let me show you something else. You know what? Imagine that you have a machine that you have trained, and it is computing rho of theta, and you are happy with this machine. It actually does well. It computes rho of theta properly. Now I'm asking you the following. It is computing the probability of the image or something related to it. How can you use it in order to synthesize an image? Can you suggest an algorithm to turn this machine into a synthesizer, into a G theta? What do you think? Or an algorithm that will use it in order to generate an image? Please give me an idea. Again, I'm asking. You have a machine that for each image, it does the computations and computes rho of x. And rho of x, as you can see here, is inversely proportional to the probability. So you do know something about the probability. What can you do now in order to make it a machine that can actually generate images? Ideas? Anyone, please?
We need to sample from that probability.
How? How? This is exactly what I'm asking. How do you sample?
Some kind of Monte Carlo.
Make it more concrete. What do you do?
I don't know.
Okay, so here is the idea. And it's
אפשר
not
אולי
far.
ללכת,
Yes, go on, Ron.
אפשר אולי ללכת בכיוון שמגדיל את
Wonderful,
P של
wonderful,
X.
Ron. This is exactly it. Let's have an iterative algorithm. Start with the random vector, which of course has a very poor value of rho theta, very high value, and start minimizing it. Remember, small is better. Start minimizing it by going through the gradient of rho. And by minimizing it, what are you doing? You are climbing the hill over the function P of X or log P of X. And so the image that we'll be producing is better and better and better looking up to the point where you stop, and that's it. And you know what you have just done? Invented diffusion models, which is again why I assume that we don't need to talk about these techniques here. Let's talk about the actual thing that happens, the diffusion models, which is so much more elegant and more justifiable. So let's just move on. Okay. Energy-based. Autoregressive methods, I don't want to say too much about them, just to mention their existence. The idea is the following. Again, we are relying on a basic formula in probability. The formula that says that if X is a vector of length n, then you can actually write it down as chain of multiplication of conditionals. Draw at random the first pixel, draw at random the second given the first, draw at random the third given the first two, etc. And this chain, we spoke about it in the review a week ago. If you can turn it into a machine that can actually simplify those conditionals, you can actually draw at random your signal, your image, pixel by pixel or patch by patch or one coefficient at a time in a transform domain, all sorts of tricks played like this. It works, but it takes forever. It's not so elegant, so I'm not so much interested in talking about it. Okay. Let's move to a different topic now. A question I asked before. Okay, you have a generator. You know what? You just given me a generator. You don't even tell me where it comes from. It could be normalizing flow trained. It could be EBM. It could be GAN. I don't care. It could be VAE, the second part of the VAE, the decoder. You have a generator, and now you are trying to say, how good is it? How do you quantify its performance? The first thing that may come to mind is, let's look at the images, which is, of course, what you would do, okay? But the thing is, looking at the images itself cannot be sufficient. Why? First of all, because it doesn't give you a quantity to compare with. So you cannot compare algorithms. But more than that, looking at images is hardly sufficient. For example, if there is a mode collapse in the algorithm, for example, if there is a region of content that is never visited, you will never know. For example, if these are face images and you never get a combination of specific skin color with specific hair color, if it doesn't happen, you don't even know about it. It's just the fact that you look at images and you are happy that they look good and you are being cheated. Another thing is you look at images and you think that they are good looking, but you don't know that, for example, some textures are compromised. They are never existent. So all these suggest that we should come up with automatic and fair measures to compare such generation algorithms. So people come up with such algorithms. It's an industry by itself, and which of course came to accompany the other industry of generators that we have just described. So we have the inception score, we have the threshold inception distance, we have the precision and recall, and we have the negative log likelihood. Let's talk about them briefly in the coming few slides. Okay, let's start with the inception score. Imagine the following. Imagine that I have a machine that generates images that are very much similar to the ImageNet. I'm specifically referring to ImageNet here for a reason. Okay, now what is it that I want my generator to do in order to make me happy? I want the images produced by the generator to have a distinct classification. What does it mean? It means that if I have a pre-trained classifier for these images that can tell me which class it belongs to, I want the decision of this classifier to be very clear. This is a dog, this is a cat. If the classifier is confused between classes, it really means that the image is not good looking. So this is one thing. The second thing is, I want my images to visit all classes. I don't want them to avoid visiting some of the classes. This is exactly the mode collapse I mentioned before. So you know what? Let's use the inception classifier. It's a very specific classifier designed for ImageNet. Let's use it in order to assess these two. And now I'm making things more concrete. Here is how we compute the inception score. Inception for this term. Inception is the name of a network. If I feed any, I'll take 50,000 generated images, xk hat for generated, and I'll push them through the classifier. Remember, the classifier has an output of 1,000 values that are basically probabilities that are summed to 1. And what I want to make sure is that those probabilities per each of the images have a low entropy. Why low entropy? Low entropy means that one of the values is really high and all the rest are really small. This gives high entropy, low entropy, very low entropy, nearly zero entropy. I remind you, you get zero entropy when this is just 1 and all the rest are zeros, and you get the upper bound when all the probabilities are the same. So again, for the 50,000 generated images, per each, I want these vectors or the output of the inception classifier to have low entropy. Lovely. In the same spirit, if I take all these vectors yk and average them, I'm expecting a vector that will be nearly flat, coming to say that I visited all the classes equally well. Okay, and that means that the entropy of this average vector will be very high. Okay, let's now take these two terms and merge them together into one expression. So here it is. Okay, so here is something related to the inception score. It's n times the log of the inception score. Let's look at this expression. This expression says this is the entropy of the average vector. It should be high. And I'm multiplying it by n. Why? Because I have here another term that multiplies by n entropies. And these are the individual entropies of each of the images. So by having high value here and very low values here, I'm getting very high inception score. Okay, this is how I compute the inception score. Let's do a little bit of algebra here. I remind you that y, remember, y is the average of yk. It's all the sum of yk's divided by n. So take this, plug it in here. The n cancels out, and you get that this is the sum of yk times log of 1 over y minus the same expression here. Now, why am I so happy about the result here? Because both summations have the same prefix yk transpose times something, times log of something minus log of something. Log minus log is basically log of the division. So here it is. Now, what is this? Anyone? What is this? How do we call it?
Kullback
Leibler. This is the Kullback-Leibler between yk and y. So basically, this is a sum of n Kullback-Leibler divergences between the average y and each and every one of the individual yks. And we want this to be really high to say, you have to be very close to zero entropy, you have to be very high entropy, and so I want very high values. So inception score of 100, 200, I'm happy. 10, 5, I'm very sad. Okay? So just to summarize, the bigger the better. And here it is. Inception score is in fact this expression divided by n and taking exponent off. And here it is written in a slightly more elegant way, which says exponent of, basically this is an expectation. Expectation of the KL divergence between what? Between the probability of yk and the probability of y. This is the probability of y given x and the probability of y. Probability of y is basically how much you visit each of the classes, and probability of y given x is how distinct you are in classifying a specific image. This is the inception score measure, and it has some limitations. First of all, it applies only to labeled data. Okay, if I'm, for example, looking at the generator that generate faces, I have no clue what to do. It is assigned, it is based on applying a classifier and looking at the output of the classifier. Secondly, it is heavily tied to the inception network and to ImageNet. So if you have a different data set, you are already diverting. And one more thing you should know, when you apply a neural network as a classifier, you cannot trust the probabilities at the output. They are not true. They are over-optimistic typically. Networks of this sort need to be calibrated. And so no one spoke about calibration here, which is very much missing. Another thing that is very much annoying here is the fact that if I give you a machine that memorized 50,000 images and just spills out these images at random, it will be considered as a perfect image, a perfect generator, which is of course nonsense. Memorizing is not a proper generation. And one last thing. We used 50,000 generated images, but we never compared them to true images. What we need to do is to do the comparison in order to show that the statistics match. We did not do any of this. So this is the inception score and its shortcomings. Let's move on. I'm moving on to the Fréchet inception distance. Fréchet inception distance basically tries to fix the main problem with the previous measure, which is the lack of distance between P true and P fake. So let's come up with a way of assessing the distance between P true and P fake. The problem is P true and P fake are very complex distribution. How can you do that? So what the people who invented FID suggested is to embed the images. Basically, take the very same inception classifier, apply it to true images, to fake images, but cut the classifier in the middle, take the vector at some specific level, call it the embedding. It's a vector of length 2048. And now assume that this embedding vector has a Gaussian distribution. So here is the idea. You take 50,000 true images, you feed them to the inception classifier, but only to the first portion of it, cut, take the vectors of length 2048, now we have 50,000 such vectors, evaluate a Gaussian from it, it has a mean, it has a covariance, just evaluate it, straightforward. Do the same for fake images, 50,000 fake images, mean, covariance, and then compute the distance between these two Gaussians using the Wasserstein. I remind you, Wasserstein for two Gaussians has a closed form. It will come in a second, hopefully. So this is the closed form for two Gaussians in the embedding space. And this is the definition of the Wasserstein in general. Don't bother reading it because we have gone through it earlier. And if the value is small, if it is 0, that means that the two Gaussians are perfectly aligned. And then you claim that the distribution of fake images is aligned with the distribution of true images. Notice that FID here can be computed to unlabeled data. So you can take faces, feed them to the same classifier. If you take the embedding, those embeddings do make sense because they capture something essential about images, which is sufficient in order to proceed. FID is not perfect. It has some shortcomings. For example, 2 years ago, there was a paper that showed that FID can be attacked. That means that I can take good-looking images that were generated from a good performing generator, change them a little bit and create a horrible FID. And vice versa, I can take noise images that are horrible, change them a little bit and get a terrific FID. And all this with attack on the inception classifier. And they came up also with a remedy for this, basically robustifying the classifier. We will not talk about it. Still, it's very much used in all the papers. We will see it a lot in the course. Okay, FID. Here is another measure, very popular measure and very elegant one. It's called precision and recall. It's not the precision and recall that you are familiar with for classification. It's different. It is a measure meant for generators. So let's see how it works. Now we talk about the supports of P true and P fake. Think about the following. Imagine that this is the support of P true. That means every point within the blob here is a high probability image, and outside it is 0 probability, okay? And here is the support of the P fake. Clearly, they are overlapping partially. The question is, how do you quantify this partial overlap? So we do it in 2 measures, the precision and the recall. The precision says the following. Take the overlap area, this overlap area, and divide it by the red area. which means it's a number between 0 and 1. For example, if it is 0.7, what does it mean? It means that 30% of your generated images are actually poor quality because they are falling outside of the bluish area. Is it clear? I'll repeat. You take the overlap area, which corresponds to good-looking images, divide by the whole red area, and so this ratio will tell you how much of your images are looking okay, looking good. If it is 0.7, it means that 30%, this is the area here and here, corresponds to poor quality images that your generator enforces on us. Okay. Similarly to it, there is the recall. It's the overlap area divided by the bluish part. And again, this time it's telling you how much of the true images you are missing. For example, if it is 0.6, it says that 40% of true images you will never visit. Okay. Now all this sounds great, but the question is, how do you compute it? Because it's frightening. How do you compute it? Here is the approach. The approach is to approximate it using spheres, and this image is somewhat misleading for a reason that I will explain in a minute. So the idea is the following. First, you go to low dimensions. You apply the very same inception machine and go to dimension 2048. So you take your 50,000 true images, 50,000 fake images, and move them to dimension 2048, where things are better behaved in some sense. Okay, lovely. Now here is what you do for the recall, for the precision. You take all the fake images and create those vectors to them. Take every one of those vectors, it's a red vector, and find a sphere that contains the 5 nearest neighbors to it of the fake images. So you have now many, many fake spheres. And why is this picture misleading? Because obviously these spheres will be overlapping, okay? And my picture doesn't show it, okay? Again, every point, every fake image in this domain, I will open a sphere around it that contains 5 nearest neighbors of fake images, and I will create many, many spheres. How many? 50,000 spheres. And then I will go to the true images, 50,000 such vectors, and per each I will ask, are you falling into one of the spheres? At least one? If so, I'm happy. Good. If not, let's count it as bad. And the relative number of points falling inside the red spheres is exactly the precision. Okay? And do the reverse for the recall, and now you have values. And by the way, 0.5, 0.6, 0.7 are the typical numbers you get. Okay, precision and recall. Again, you'll see them a lot in papers. The last measure is somewhat confusing. It's called negative log likelihood. I will not say too much about it. It goes like this. If your machine, by any chance, can evaluate the probability of the image, not just generate it, then you could compute the minus log of it. So tell us the minus log of these images on average. This is it. Average the minus log. Look, I'm averaging over all the images I'm generating. I'm also averaging over the dimensions. And I'm taking the log here with base 2 in order to talk in terms of bits. So this is called the negative log likelihood. Okay? If you could compute this, go ahead and compute it and you'll get a value. And I'll tell you, this value for images is going to be 2, 3, 4. These are the typical numbers. And the smaller, the better, which means that your images are more probable to exist. This is strange because if you compute the negative log likelihood, you basically believe the computation of the generation in itself. So it's a bit problematic, but people use it nevertheless. Okay, so images that have low NLL are more likely to exist, and we are supposed to be happy about it. By the way, this should remind you of an empirical assessment of the entropy, but who cares? And what I'm showing you here is a table I copied from a recent paper, a table that shows many, many generation models. And they are of variational autoencoder type, flow, autoregressive, diffusion, that's all. GANs are not here because they cannot have NLL. And what you see for different data sets, CIFAR10 and ImageNet, they show you the NLL for them. And the smaller, the better. So they are so happy to deliver the number here and say, we are the best in terms of bits per dimension on the test set. So this is the NLL, and I'm not going to dive deeper into this. Okay, one last topic, and with this, we will finish the lecture today. Imagine that you have a generator, G theta of Z. Somehow you got it, and you are happy with it. How can you use it to solve inverse problems? So here is a basic answer to this question. Okay, you can use it to solve inverse problems, and I'll give you the most elementary approach that can be thought of. Just to remind you, there was an ideal image X naught that went through a degradation C plus V random noise. You get the measurements Y, and you are trying to make your way back to X naught. And I remind you that in the previous meeting, we come up with the following expression for getting the estimate of the map, the maximum a posteriori probability. It says that you have to find X that minimizes these least squares, but with the regularization that takes the probability of X into account. And since this is the log of P of X, then this is basically the energy in the Gibbs expression. All this is just background. Coming back to our question. Okay, now, how do you take a generator and use it in order to solve an inverse problem? Please, your ideas. What do you think? What can we do? Intuition only. Ideas? Anyone?
You can use it to compute the MMSC, for example.
How? How can I use the generator to compute the MMSC?
So assume that it approximates P of X.
No, it produces a sample.
Ah, okay, yeah, you're right, yeah.
It is a sampler. Okay, if it computes the P of X, I'm done. But it doesn't. It's just a sampler. So what can I do? So here is what people came up with. Remember, this is what we are after. One option, very simple option, in a second, is to take this expression and replace X here with a generator over Z and optimize with respect to Z. Okay? Optimize, minimize with respect to Z this expression. Forget about the yellowish part, just this. What is it saying? It says the following. Hey, I'm trying to figure out who is X here that will multiply by C and get something close to Y. There are infinitely many such X's. But since the generator is smart and for every Z it produces only good-looking images, it is already narrowing down the solutions. And so by minimizing this, I will find a good-looking Z. No, I will find a Z that hopefully will behave like a random vector, random Gaussian. And when fed to the generator, it will make a good-looking image. Then comes the yellowish part and says, you know what, if you are interested, I can actually push the Z here towards the origin to make sure that it does look like a Gaussian. And so this is one way of doing things. Minimizing with respect to Z here and eventually taking G theta of Z, and you end up with a solution that is basically an output of a generator. Is it clear? I hope. I hope it is clear. Another option that people played with is to do almost the same thing, but use the other expression, rho of X here. Plug G theta also to rho. Now, where do you get rho? The idea is go back to the classics. Use a rho from the classics. Use something like sparsity or wavelets or total variation. Yes, it is somewhat old and somewhat dumb in a way, but it does help because it serves as a lovely regularization to your solution, and it does produce beautiful results because eventually your generator produces good-looking images. This is how it is trained. Now, here's the thing to understand. Whatever you do, this or this, when you minimize with respect to Z, you have to back propagate through the G theta. So you have to go back and forth through G theta. And this is exactly where normalizing flow could have been amazing, because I remind you, G theta has an inverse, something that most generators do not have. So in such cases, the optimization is less cumbersome, let's say. Okay, so this approach works well and it does deliver. Okay, so just to summarize, the holy grail of image processing is identifying P of X and then leveraging it. This is what people did in several decades of massive activity. And it's not just true for image processing, it's true for other fields as well. The classical approach kept guessing all sorts of structures for P of X, and we have seen the evolution of those methods. The more modern approach replaces it with the design of generators that are truly amazing in their performance, and then plugging them in all sorts of ways. Some of them do provide the computation of P of X or something related to it, but it's relatively rare to see this happens. And yes, if you do have such machine that generates, it doesn't imply that you do know how to compute P of X. You can't in general. What we will do in this course is to come up with yet another generator, a generator that is much easier to train, a generator that is much better performing than everything else that we have seen, including GANs, a generator that is mathematically well established. And this is the diffusion approach. And on top of all this, we could leverage it to other needs. So this is what takes us to the next chapter of starting to discuss diffusion models. This is it. So I'll stop today, and there are 10 more minutes. I'll stop now, and we will continue next week.